read the Nature paper on that, and we will also, I can also try to answer to your question if necessary. Okay, so now we definitely enter into the tertiary, and we will examine details with Paleocene thermal maximum. And here I put a question mark. Is it the best analog for the actual warming? And to try to answer to that, I will give you some example, some insights from Europe, Egypt, and also we'll spend some time talking about the PTM in India, because you have very nice outcrops in India, which include the PTM. Okay, so first of all, what is PTM? Okay, this is a Paleocene thermal maximum. This title means a very simple thing. It means that it was quite warm, very hot, okay? And here this is more or less the content of what I want to present you. So again, we will talk about the GSSP. The acronyms of GSSP is Global Stratotype Section and Point. This is a definition of the base of the stage, and generally we use good markers for that. And here you will see that what has been proposed and ratified, this is to use a huge delta C13, so carbon isotopes, negative shift, which is occurring right at the PTM boundary. And after we'll talk about the events that occurring during this time, and evidently about timing, and after we will go through the evidences of the warming. We talk about micropaleontology, but also paleontology. We talk about the mammals origination, and it's here that I want to take you in India, and to show you the section on which we have worked. And after we'll talk about stabilized isotopes, clay minerals. All this evidence is showing that huge event, huge warming was occurring during the PTM around 55 million years ago. And after we will discuss about the cause and mechanism. And here you will see that it's not only a question of volcanism. Volcanism is clearly behind that, probably the trigger at the beginning, but there is something else if you want to explain the huge negative delta C13 shift that we can observe. And after we'll try to talk a little bit about the implication for the futures, but we'll do this mainly when we were talking this afternoon about the Anthropocene. Okay, so after we'll try to answer, is the PTM a good analog for the present warming? And I can already tell you yes and not. Yes, in terms of huge warming, this was quite fast, but clearly not as fast as the one that we had by now. Okay, so this is GSSP. So the GSSP, this is a standard stratotype, and you can see here that this GSSP is located here in Egypt, close to the Nile River in Luxor. And I think it's a big error, because politically Egypt is not very stable, and the access of this GSSP is very restricted, because this is in fact quite dangerous, and if you want to sample that, sorry, you need the help of some soldiers. You need some protections, because there is a lot of, let's say, troubles linked to Muslim fundamentalists. And what they did last years, or 3 years ago, they destroy part of the stratotype, which is that one, and they destroy the small museum that was close to the stratotype. So it's clearly showing something when you want to choose a place to locate a GSSP. We have to be very cautious about the politics, because we don't have to do that in some, let's say, unstable country, politically speaking. And this could be really a problem, because now the access here is very, very restricted. So this is a definition of the PETM, of the official GSSP PETM. And here you can see that, this is a base of the Eocene, and the first stage of the Eocene is named Ypresian. The age is 55.8 million years ago, plus or minus 0.2. We can also recalculate this age using astronomical cycles, and the main correlative marker that we are using everywhere, this is the base of the negative carbon isotope excursion. And the location is in Luxor. As I said, it's already published in several papers. Even if this thing is a little bit problematic, it's still, it contains the good marker, that's to say, this stabilized upshift. And this stabilized upshift, you can see it here. Look, this is really, really, really negative. More than 4 per mil excursion. It's not the only one, but this one you can see is really abrupt and quite fast, as you will see. Okay, now this is part of a story which is very important, because this is probably the Eocene. Here is the last period of the greenhouse. This greenhouse, so very cool, warm period with a lot of rain and a lot of weathering, was clearly dominant during the Jurassic, more during the Cretaceous. During the Cretaceous, we have all this volcanism activity that I show you when I was presenting you the chapter on anoxic, oceanic anoxic global event from mainly Cretaceous. And when you enter the tertiary, as you can see here, this is a very nice paper from Zakos. And as you enter here, you can see that, this is the temperatures is here. Paleocene, Eocene is still quite warm, but when you enter into the Oligocene, that's to say 34 years ago, it becomes to be cool and cooler and cooler. And this, as I'll tell you, has probably something to do with more or less uplift of the Himalayan chain and the Alpine chain, leading to more weathering and a drawdown to CO2. But what you can see here, that this is a location of this Paleocene-Eocene thermal maximum. So here on that things, I called them late Paleocene, because at this time the PETM, the Paleocene-Eocene boundary, was not defined. That's why sometimes the name can be different. But what you can see, it's a huge straight line here, an increase in temperature from 6 to 8 grades centigrade, which is really a lot. And after, you can see that the upper part of the Eocene that you have here is also marked by a climatic optimum that people call ETM2. These two events, you can find it in some sediments in India. I will show you this later on. And already here, we will go back to that. You can see that this warming here, so if you look to that, you can see here that these are more, let's say, negative or less positive, if you want, values. So oxygen isotopes are really indicating a huge warming here, a rapid warming. And you can see here that there is this delta C13 shift, which is really incredibly strong. And it's a question of several per mil of negative shift, which is followed by another one. Okay? And after this was the last episode of the greenhouse warming. And after, during the tertiary, we are entering in a very different state of the biosphere. This is cold house, ice house, starting mainly in the Oligocene, well, now we are here. Okay, and you can see here something that we will discuss more in detail this afternoon. Here you can start to have ice sheets first on Antarctica and after in both poles, Antarctica and Arctica. And as I said, this cooling is mainly linked to several oceanographic change, but also to the establishment of the Himalaya chain and Alpine chain. The first one linked to the Indian-Asia collision. The second one, I showed you this yesterday with the paleographical map to the collision between Africa and Europa. Okay, so this is a really crucial time. Okay, because by now we are somewhere here, and you can see here that we are in a period where we have ice on the two hemispheres. But I will show you this afternoon that this is changing very, very rapidly, and this is quite puzzling. But note here that probably one of the main triggers of this hot house, of the transition from hot to ice house, was probably tectonic activity. Okay, so now a little more details. I show you some picture from a place where by now, unfortunately, it's really impossible to go. This is the Sinai Desert, which is close to the border between Egypt and Israel. And here, by now, all this territory is occupied by Al-Qaeda. So I don't want to go there anymore. It's a little bit too dangerous. I don't want they cut my head. Okay, this is a place where, unfortunately, it's impossible to go by now. And you have a very nice outcrops here, showing a transition from the Cretaceous here, with a choke. The KT boundary that we have here with an iridium layer again is just here. And on top of that, you have the Paleocene-Eocene boundary, which is just located here, close to the base of the arrow here. And this one is characterized by an iridium anomaly. This one is characterized in that place by organic-rich sediments, which have almost no calcite again. So some kind of dissolution horizon, as you will see. And this huge cliff is Thebe Formation. It's an Eocene formation, which is very well known because this cliff is a cliff all around the Nile River, which in which people, older Egyptian, former Egyptian, were taking the big stone to build the pyramids. Okay, and this cliff is almost only made by nummulites. Nummulites, you know what it is? What it is? These are really big foraminifera. Remember, I was talking about fusilinids, which has a big foraminifera from the Permian. And now the nummulites are really the big foraminifera from the Eocene. Again, they can reach more or less a size like that. This is just one unicellular organism. And again, probably it needs some help of symbiotic algae in order to produce so much calcite. Okay, so these are the two boundaries. In terms of paleogeography, you can see that there is not so much difference between the KT and PE boundary. You can see here, the main difference is probably the location of India. Here, India was passing through the hotspot, quite far still from Asia. And during the PETM, This is not all the time of the collision, but the subduction was going on. There was maybe a possibility to cross from Asia to India during the PTM, but we'll discuss that. Maybe, but probably a little bit later into the Eocene. So there is not so much difference, but there is a big difference. You can see here to the north, this is the opening of these two straits in North Atlantic. This is a rifting period with a huge volcanic activity. This is the North Atlantic volcanic province. When I say huge, clearly it's not comparable to the Deccan or the Siberian traps, but this was quite a big volcanic activity, as you will see. Okay, so in terms of stable isotopes, the Paleocene thermal maximum that we can call PUTM or ETM1 occur in fact here. You have this huge here warming that you can see, which correspond to this huge negative shift. And after, you can see that there is several increase in temperature, ATM2, and some early Eocene hypothermals, meaning increasing temperature, and hypothermals means decreasing temperature. So this was a time where you have a lot of this sharp, sudden increase in temperature. But the main one clearly is that one. This is the one that we talk. ETM2 is also quite important, as you can see. It's also quite a negative shift that also we can find in India, namely in the lignite mine. Okay, now, as I said, this is the Paleocene-Eocene boundary, and the last stage of the Paleocene is the Thanetian. The first stage of the Eocene is the Euphrasian, and if we put some numbers about, because clearly, if you have this negative shift of delta C13, it means a huge perturbation of the carbon cycle, okay? And this perturbation, if we put some number in terms of timing, if you take in account all, let's say, the total duration of the perturbation plus the recoveries, 170,000 years. This is not so long. The duration of the carbon perturbation is around 40, 70, let's say, 1,000 years. The starting point, more or less the onset, is probably quite sharp and fast, around maybe 5,000, 6,000 years. But compared to the present carbon perturbation, clearly this is longer. But anyway, here you can see that this is a course which is very informative, because the white things here are calcareous, almost a chalk ooze with a lot of foraminifera, which is suddenly, and this is a deep record, probably deposited in something more 1,000 meters deep, interrupted by this yellow to brown layer, which correspond to a dissolution event. Okay, there is almost no more carbonate here, and this is really one of the important clues that in the deep sea you are losing the carbonate almost everywhere during this period. So this point to acidification clearly. And the interesting things with the PETM is that you can find it in the ocean, in the marine sediments, but also is very well expressed in continental sediments. And here I will spend a little more time to show you some of the outcrops. The most famous one, the first one that people have seen, is in the Bighorn Basin in USA. And well, you can see here that you have a delta C13 shift. This is somewhere here, and these are badlands which are made of a succession of paleosols. And these paleosols are yielding very nice mammals, bones, and the modern manal bones. But we'll talk about that a little bit later on. Another place that is really interesting, this is Spain, if it works. Yes. Oops, sorry. Spain. So here we are in south of Spain, on the Spanish side of the Pyrenean. The Pyrenean, because probably you're not very familiar about this geography, this is Spain here. And the Spain is the boundary between Spain and France here is marked by the mountain chain named Pyrenean. This would be the Mediterranean Sea, and this would be the Atlantic Sea, okay? And here this is a view of this PUTM transition. You can see here some, I have to go back, yes, no, oh sorry, oops, okay. You can see here, these things are located here, and you can see they are clays, red to yellow clays, which contain a lot of carbonate nodules. And these are paleosols. It's a succession of paleosols, which is really interesting because these paleosols contain some nodules. And these are carbonate nodules, which are links to roots, because generally plants in some environment are more or less expelling calcium carbonate along roots, and after it forms this kind of nodules. And these nodules are interesting because we can measure stable isotopes, oxygen and carbon, and get some nice curve. And this is a way that you can find the PTM negative excursion even in the continent. On top of that, close to that cliff that I will describe later, you see a change to fluvial to lacustrine sediments. Close to the PTM, it means that this is more humid. Just so it's more humid, more water. It means that you increase the riverine influx, that you increase the rain, probably more greenhouse condition. And on top of that, suddenly, there is something here for this area, which is very extraordinary deposits. It's a conglomerate. This conglomerate is made by a poly of multiple origin. You have boulders and pebbles from dolomitic to quite deep basalt, coming from the Pyrenean here. And this sheets of conglomerate is covering all this area over kilometers and kilometers. It means that it's an extreme event which affected a big part of this part of the Pyrenean. And we calculate, because you can calculate more or less using some kind of measurements because these are channels, and these channels here, if I can find it, you can measure more or less the depth of the channels, thickness, and more or less the length, and we can deduce here that this kind of extreme event mean that you have very, very heavy rain, and mean more or less 3-4 times increase of the general river discharge during this event. And this, as you will see, corresponds to the PTM event. On top of that, you have still some paleosols, and above, this is very nice, with very nice ripples, just showing that we are entering in some kind of marine condition marked by these limestones here. Okay, and if we run some stable isotopes, delta C13 stable isotopes, we can see very interesting things, especially first that the continental section sometimes may be very complete, and may sometimes show some details that you don't see in the marine section, as you can see here. I will explain this now. So this is a Bighorn Basin here to the left. This picture, these things may work normally, yes. This Bighorn Basin, this is that section. You can see an interesting things here. There is a negatives delta C13 shift followed by a long negative one and after more positive. In Spain, this is a section that I just show you. You have also a negative here and a long negative here. And you can see that the onset of the long negative is cut by this conglomerate that you have here, okay? So this things is a pre-PTM event. So this pre-PTM event is quite interesting because it corresponds to something that you don't see, for example, in the GSSP, the marine one. You have only this big negative shift, but this things is not clearly present here. And these things has been found only in continental sediments, with an exception here. This is a very shallow environment from Maryland in USA. So it means that here you have maybe a pre-PTM event which will trigger the huge negative event, very negative delta C13 event. Okay, a little bit more in details. You can see here, I will just show you especially that for the picture here, because you can see that these are the small nodules on which we are measuring this oxygen and carbon isotopes. We are also measuring the organic carbon stable isotopes, and you can see here that we have different shape, different size. Generally, we are trying to take the similar ones, and you get for the delta C13 here this very nice curve, okay? So meaning also that you can see also here from the claret conglomerate that you have also more negative values here, indicative of probably a change in the hydrogeological cycle and the warming. So it means that everywhere, almost, as you will see, you have this huge event, whatever you have, continental sediments, marine sediments, deep or shallow. Okay, so what are the main characteristics of for that period? So we already have seen that clearly you have a very sharp negative excursion in both oxygen and carbon isotopes, meaning that well, you have really here an addition of very light carbon in order to get this delta C13 negative shift, and here you have a huge warming in order to get this oxygen negative shift too. You can find it in marine and continental domains. This is very fast. We'll discuss this later. And after, if you look at the paleontological record, it corresponds to the extinction of deep benthic foramnifera. What I call deep benthic foramnifera, these are the foramnifera, the benthic, living on the seafloor, but at a depth of 2 to 3 kilometers, okay? If you take the big one, living in the shallow condition, in a very shallow water, 10, 50 meters depth, they don't suffer any extinction. Only the deep one. Okay. This is very important for the explanation which will follow. You have amongst planktic foramnifera, there is no extinction. Surface, we are not suffering. Contrary, you have a lot of warm water, a lot of nutrients coming in, and they really like it. This was so warm that you have here, as you can see here, a temporary presence of thermophilic organisms, for example, turtles, alligator, palm trees, as plants, as trees, up to Arctica. Just think about that. It was really, really hot for a while. And this corresponds to what I call the event. This is the mammal origination event. This is the first occurrence of the modern primate, for example, which are our ancestors. So we can maybe say that thanks to the PTM, we are here, okay? And so it's a very important episode. And as I said at the beginning, this is the warmest period of all the Cenozoic, all the tertiary. This is the last period of tertiary which was so hot, 6 to 8 degrees warming, and interestingly of deep and surface water, and you have a strong increase in humidity. And I will show you all the evidence now showing that we have this warming and high humidity. Okay, in terms of timing and intensity, we can, there is not so many ash layers apart in Denmark and the Caribbean, close to Central America, which allow dating. But what people use here mainly, this is a cyclostratigraphy based on magnetic susceptibility, because this magnetic susceptibility here is depending of some digital input, which will vary following the cycles of Milankovitch. So you can put this a precessional, okay, cycle, which can allow quite precise dating, as you can see here. And this is really a global event. Why I say that? This is because if you compare, for example, here two curves, which represent two records, which are completely located in different places. This one here is in Florida. The other one is in South Atlantic. This is the Weddell Sea. And you can see that this is delta C13. You can see that you can here show all the details of the curve are correlatable. It's a fact that you start quite abruptly. There is maybe this pre-PTM event here, could be, but it's more clear in the continental sediments, and the period of very negative, the recovery, and so on. And there is many records which show exactly the same. So it was really global at more or less the Earth scale. In terms of warming, it's quite interesting to see that, well, if you have quite a lot of foraminifera, benthic, deep planktonic, you can do what we call a ranking of the temperature of the mass water. So you can define, for example, by using the planktic and benthic foraminifera, what we can call, for example, here the Tethys bottom water, the Antarctic intermediate water, and the surface here water. And the interesting things here, that you can see that this is positive, negative, okay? And you can see that all this mass water, whatever deep or shallow they are, all more or less record a huge warming. And you can recalculate here the temperature. You can see that this is an increase varying between, let's say, 4 to 8 degrees. This is huge, okay? And just remember that the deep water, oceanic deep water, is also warm. This is quite important in order to understand the scenario of that crisis. So the warming was, let's say, everywhere. A little bit like now. That's why the comparison is maybe quite useful. Okay, so for example, here, this is a place in Uzbekistan. I went there with a PhD students in 2002, I guess, some time ago. This was really the beginning of the opening of all this land, because before, this was during the Soviet Union, it was almost impossible to go there. You need so many visas, almost impossible, especially because this was area where the Russian put a lot of atomic bombs and things like that, especially in Kazakhstan and Uzbekistan. And so it was quite difficult to go there. But by now it's possible. And here, these are new outcrops. You know why? Because these outcrops are located close to the Aral Sea. You know what happens to the Aral Sea by now? You know where is the Aral Sea? It's in Uzbekistan. It's an internal sea, but by now, do you know what happens? There is no more sea almost, because this Aral Sea is drying out completely for several reasons. Warming, for sure, but another reason is the fact that since more than 50 years there was overuse of the water all around, and the big river flowing into this Aral Sea, all the water of this river was more or less used for the cotton field, and meaning that in absence of water coming into the sea is just drying out. Okay, and this for the geologist, this very bad things is good, because it allows to have quite a lot of new outcrops. And this is a new outcrops that we visited in 2002. And here you have the warming. These are oxygen stabilized stops, which correspond also, it's not on that picture, to a delta C13 shift, which is quite negative. Interestingly, you can see that we separated the planktic foraminifera in cold water genera and warm water genera. And here you can see that the cold water genera during this crisis are really, really low in terms of quantity, and they are replaced by some Igorina, which are planktic foraminifera, which really like warm water. And there is also some blooms of dinoflagellate, which are kissed off unicellular planktic algae, and these dinoflagellate also are really blooming. It means really that we have an increase in surface water productivity under very warm condition. A little bit against like now. So in surface water, I say in the ocean, we can say that everybody was quite happy. But it was clearly not the case in the deeper ocean for the deep benthic foraminifera. And here you can see, when I say deep, these are the foraminifera living, let's say, at a depth of 2 or 3 kilometers, okay? And these foraminifera got extinct for quite a lot of them. In fact, as you can see here, almost 50% of them, forms like Gavelinella got extinct, but it's not the only one. So something is happening in the deep ocean. What? We will see this later. It's a little bit like an investigation here. We are looking really about the trigger. I'll give you some evidence gradually. But on the surface, as I said, planktic foraminifera really like it. And you can see here on that graph to the left, this is the benthic, this corresponds to the benthic foraminiferal extinction, the deep one. And you can see here, this is a species turnover rate among the planktic foraminifera. And you can see that you have a huge number of species, which are appearing during this time in the surface. So the planktic foraminifera are increasing in diversity during this time, contrary to the deep benthic. And now I will move to land, and we'll speak a little bit more in details, because we work quite a lot in India about that. That's why I had that. But this is not in your notebooks. Sorry, because I did it this week, and moreover, this data are submitted. They will be published in the Journal of Asian Geology, but it's not totally the case. That's why I didn't put it there. And here you can see, well, this is a general figures showing more or less the evolution of the mammals. The Paleocene, you can see that was crucial for the mammals' radiation, especially the modern one. And, well, we are here, okay? And you can see that the Paleocene, this is a moment where you have a huge diversification. That's why I call this like the mole event, like the cow, if you want. There is no cow here, clearly. But the mole event means mammal origination event, okay? And it took place during the PTM. And now I just want to discuss a small problem here, which became at the end very nationalistic, if I can say, because this is a main question. All these nice modern mammals, you know, were migrating, and there was the idea that in fact the first modern mammal were originating from India, and after were migrating in Asia, in Europa, in the US, okay? And this was because, in fact, before India was attached to Africa, and people are thinking that when India were moving, they were moved with some kind of mammals, and these mammals give rise to the modern one, and after were migrating throughout the world. What I want to show you, and a lot of specialists were clearly against that story, the main, let's say, supporter of that theory is Sunil Bajpai. Sorry for him, but it's wrong. And he really wanted absolutely that the mammals were originating from India. But I will show you, by using some data from India, but also from all over the world, and using the stabilizer top curve, you can prove that in fact the mammals were originated from Asia, from China mainly, and after to Europa, and after to US, and finally to India. And this is quite correct, because if you look to a paleogeographical map, it's clear that at the PTM, India was quite still a little bit far away. It must have been very easy to cross, but it has been possible later on, as you will see. Okay, so this was just a title of a talk that I give to the last international meeting to paleontology in Paris 1 or 2 years ago. In fact, these data are coming from this guy. This is not this Indian family, but this was as an outcrops very close to a school. So we had a lot of children very curious here. And the guy that you see here with the blue shirt is Hassan Kozem. It's an Egyptian guy who did his PhD with me in Lausanne. And he was especially working on the PTM and especially in India. Okay, and why in India? Because in India you have a lot of lignite mine, which are Paleogene in age. You know that in India you have two main sources for the coal, and coal is very important in India because it's a source of energy for sure, in absence of hydrocarbon reserve. Because in India there is not so much gas and oil. There is some, but not so much. But there is a lot of coal and lignite. Coal, you have a lot in the Permian. We discussed a little bit about that yesterday. But the lignite layer, you got it especially during the Paleocene and the Eocene. And here, this is just a view of mine. I don't remember the name of that one. It's maybe Panandro. I'm not sure. And in fact, the aims of part of this thesis was to determine the age of the lignite deposits in Western India and its links with the hyperthermal events, meaning that we were thinking, and we are not alone, already some Indian researchers were more or less mentioning that as this part of the lignite are maybe linked to the hyperthermal event, the PTM event. And after the question was what is the relation between modern mammals migration and the Paleocene-Eocene thermal maximum, and especially in India, the question of the migration to or out of India. Okay, so what we did here, we sampled and we visited a lot of lignite mine, and I have to say that it's very easy to get the permission, and there is some guest house. These people are very friendly. And it was really possible without any problem to sample all these mines. And we sample mainly mines from Gujarat here. And we went to Banvagan, we went to Vastan, Tageshwar, and Panandro, which is close to Kutch. Okay, and this, let's say, lignite mine have probably something to do with the Kambe basin. This is a rift which creates some depression where you accumulated this mine. Okay, but before that we came, so quite a lot of work has been done. And here, for example, this is a Western mine, which is this is a most known mine for the lignite, because this is the first time that modern mammals have been found in India. And really moderns, the same as us, but it's not man, but for example, the primate, okay? And here, this is a work by Samantha et al. I think she was at ITT, not sure. And she showed already that, well, there was some negative shift that she interpreted as a PETM. And you have here the ETM2, the second negative shift. So this is warm, this is another hyperthermals. And this has the lignite seams. And generally, you know, they count the seams from the top to the base. And generally, the PETM is close to the seams 2, ETM2 to the seams 1. And these are the things that they are sampling. And sometimes it's difficult because I understand them. They dig big hole, really big, very fast. And I just remember the first mine that we visit was in close to Barmer, close to Rajasthan, the Jural mine. And in fact, we sampled this mine accidentally because we had nothing to do for 2 or 3 days, because the outcrops, the KT outcrops that were not KT. So we decided, because I had the feeling that this lignite has something to do with the PETM, to sample this Jural mine. And we found in a preliminary examination this some kind of delta C13 shift, and decided to go back because the base of the mine was missing. And when we went back, the mine was completely infilled. I say, oh, it cannot be possible. We just went by flying from Europa and so on in order to look for some samples, and there is no more mine. So I asked the director of the Jural mine. He said, oh, but it's not a problem. We have another one that just dig a big hole. So it's very fast, very, very fast. This is the Anthropocene. And what we did is to sample this first mine, for example. And sometimes it's not so easy, you know, to go down here. You know why? Because, well, I understand the coal specialists, when they reach that one, they just stop to dig. So several times we ask with a big machine, they agree to go down for, let's say, 5-6 meters down in order to sample what you have below. And so interestingly, you can see that you have that, and Vastan, when we went to Vastan, all this part was already covered, unfortunately. And we had only that part, and that part is quite interesting, because you can see here that all this is continental with lignite, these are seams, okay? And here you have in all this place the same event with the nummulites, but I think a lot of people know here. And this is Eocene, and this is ETM2, which is marked by this quite long negative shift in delta C13, which is all here clearly measured on organic matter, because there is almost no carbonate. So the benthic from Nifera support an early Eocene age for the upper part of the Western mine. And here note this star, it's quite important. This is the first modern mammal. And you can already see here that this first already mammals appears above the PETM event. Okay, so they postdate the PETM event. So we did, so as the Western was infilled, we went to the Tageshwar mine, which is quite close by. And this one was quite rather complete. A lot of TOC, clearly, as you can see here. but the most, which are mainly made of very nice organic matter from continental origin, which is not very original. But the interesting things here is again in Tageshwa, the presence of a very nice shift here in delta C13, followed by the longest shift here. This is a PETM, and this is the ETM2, and the mammals are occurring somewhere here. Okay? Again, they post-date the PETM in that section. Okay, so another mine. This is the Jiral mine, and this is in Rajasthan, Barmer district. And again, you have very nice, and this is a part where that people very friendly dug for us. And here you have the PETM and probably the ETM2 here. And this one is maybe already Miocene, who knows. But interestingly here, we have some dinoflagellate, we have some pollens that Bandana salmon from Nagpur, it's not so far from here, also determine, and she determined both Paleocene and Eocene Palinoflora. There is no modern mammals in Jiral. Nothing has been found. There is a fauna which mainly made of fish bones, but also snakes and things like that, but not really a big fish. Okay, now we can correlate these things, okay? And here what we know, that this marine interval, because if you have numulite, it means that this is marine, okay? No problem. So this is an incursion of the sea level transgression that you can follow in almost all this mine, and especially in Western and Tageshwa, and the fauna is very nice. And you have clearly also the PETM anomaly, which is very well marked and correspond also to a very special palinoflora that Bandana salmon from Nagpur determined for us. So it's without any doubt, this is a PETM, okay? So it means that you can correlate all these sections, and you have the PETM here, which is very well expressed in continental, corresponding to the second seam, okay? And this PETM is here, very well expressed from Panandro, Balanga, Western, Tageshwa, and so on. And the ETM2, which is present also problem everywhere. And this ETM2 corresponds to a marine transgression, bringing the numulites here. Okay, now the question is, what about the mammals? And here I will show you, I will start to show you first a very nice work from Thierry Smith from the Royal Academy of Belgium. It's a paleontologist, specialist of mammals. So the hypothesis, I just remember you that the hypothesis is that a modern group of mammals like ancestor of horses, deer, goats, primate, opossum, like marsupials, swept across the northern ecosystem, replacing more ancient mammals in their wake, okay? The problem, do these mammals originated in India? If it's the case, their fossils should appear earlier in India than in Asia, North America, and Europe. And so you have to compare this timing. The solution is to use stable isotopes, to use the PETM carbon shift, and to see if the fossils are below, at, or after. And what you can see here, I don't include India, which is here on that. This is a former paper by Thierry Smith et al. And he showed that in China, for example, the mammals occur at the base a little bit before the negative shift. If you go to Europe, it's into the negative shift, well into. And if you go in USA, this is a little bit above. So clearly, this migration was from Asia to Europe and to US. And now we have to add India. And if we had India, what you can see here, this is a correlation that we have, the PETM, thermal maximum, and the ATM2 thermal maximum corresponding to the appearance of these nummulitis burdigalensis that you have almost everywhere. And well, if you compare now when, for example, at Takeshua, these mammals are occurring, the same in Vastan, you can see that it's well above the PTM. So now the new image is the following. It means that you first initiate the origination in China, then in Europe, then in US, and almost at the same time maybe in Asia, which agree better with the plate tectonic, because at the PTM by itself, India was maybe a little bit too far from Asia. So now here we try to calculate a little bit, in fact, the lag between the PTM and the appearance of the mammals. It's not easy to do, but in China, in Asia, it's clearly a few thousand years before, and here, you know, it's 20, 40, maybe 50 after, and here almost 300,000 after. So now this cartoon shows you more or less what we are proposing. You first well, have the first modern mammals in Asia, and after in Europe, and after in America, and finally in India. This is what we have here. What does it mean? It means something which is important. Why do you have such a migration toward high latitude? Well, because these animals were just following their food. Because I will show you that the PTM events correspond to generally a move of the tropical belt toward higher latitude. I told you that in Antarctica, in Arctica, there was some palm trees, alligator turtles, it was really warm. And this allows, very probably, to all this fauna to migrate, because they are migrating with their food. Because this place, as you will see, during that, if you have an expansion of the tropical zone here, higher here, higher here, this part became a little bit more arid. So they have to move, okay? And this is just a nice cartoon showing a little bit how was the environment in India during this time. So this has been done by these PhD students. The PTM in India correspond to the gradual establishment of wetland, and you have increasing greenhouse condition and some vertebrate communities. And this corresponds to the deposition of the first seam, lignite 2, in the mine that we have more or less studied. And afterwards, after the PTM, mammals migrate from Asia to Europe and North America, and finally to India. This is a Murray event, and you can see here all these mammals invading India, and this would be the position of Western and Takeshua. This fauna includes the earliest modern mammals from the Indian subcontinent. And the earlier Sen ATM2, here we have clearly a change. Well, there is probably repeated release of greenhouse gas. The greenhouse conditions are going on, and we have transgression which more or less invade all this area, and bringing the nummulites in some very shallow marine environment. So this is more or less what we think our interpretation of this place. So these are more or less our conclusion for that. So we have the establishment of the wetland environment during the late Paleocene and Eocene, which is quite interesting. It means that it was really a greenhouse period, triggered by warm and humid climate. If you have cold, it's humid. There is no way to produce coal in arid condition. Modern mammals migrate during the PTM towards the high latitude, but they reach India later after the PTM. So this confirms, this supports the into India hypothesis for the mammals that main of the paleontologists, at least in Europe, all the specialists, mammal specialists, are really thinking that this is an into India and not an out India that we get for the first mammals. Okay, So now, if we go on a little bit, we have very humid condition, as I said. If you have peatland, if you have all these things, and this is very well marked, for example, by the presence here. This is a delta C13 curve with the, it's not LPTM, means late Paleocene thermal maximum, but this was a time where there was no GSS speed, so this is a PTM, if you want the same. And you can see here this huge warming corresponding to an increase of kaolite. Here, this is a ratio between kaolite and illite. Illite is a mica. And mica is resulting from physical weathering, kaolite from highly chemical weathering. You can see that in very high latitude, more rises really in the Southern Ocean, close to Antarctica, you have warm and humid condition. And with second former PhD students, Marie-Pierre Boll, we have in fact studies a lot of section all around the Tethys in terms of clay minerals. And what you can see is quite interesting. The Danyan, so what more or less the first stage of the tertiary right after the KT boundary was quite humid all over the Tethys. This is these red things that you can have here. And well, during the last stage of the Pliocene, you have a change to humid to seasonal condition. And you can see that these red dots here are moving downwards and upwards. This is just a migration of the tropical belt toward higher latitude that you can see, which was quite complete in the lowermost Eocene. What does it mean? It means that at high latitude you have more and more kaolite, so it's more and more humid. So it's really an illustration of the migration of the tropical belt towards high latitude. Okay. Okay. Now we have to start to understand why. What are the causes of the global warming? And here, clearly, again, this could be volcanism. And I will just go back a bit fast. This could be volcanism. These are the main source of CO2. These two ones are linked with volcanism. This one is a little bit different. We think that India is closer and closer from Asia, and you have a lot of paralic peatland here, as I said, which may, by oxidation, also link to a lot of CO2 into the atmosphere. But these two things are more important, and especially that one. This is North Atlantic large igneous provinces, and this was a rifting. It's always the same story. We have seen that for the Central Atlantic, we have this camp occurring at the end of the Triassic, leading to the mass extinction of the Triassic-Jurassic transition. And here, to the north, we try to open the North Atlantic. And, well, this clearly may increase a lot the CO2 into the atmosphere, especially in high latitude, and may explain high latitude warming. And here this is a table showing more or less the age. The red line here is the PTM, so this is the red line corresponding to this huge negative delta C13 shift. And here you can see that in Greenland, especially in Faroes, but also in Denmark, we have quite a lot of volcanism which are preceding, coinciding, and sometimes post-dating. And remember yesterday, we have used mercury as a proxy in order to recognize volcanic activity into sediments. Remember that I told you that mercury has 1-2 years resident times. It can be ejected up to the stratosphere and redistributed over a long distance. Well, North Atlantic magmatic province was not the Deccan, clearly, but was quite huge anyway. And for example, if we go back to that section that I described in detail, this was the one in Spain here, and which is located here. And this was close to Pyrenean mountains in some continental area. If you go on that direction, this is deeper. And here again, you can see the delta C13 shift that you have here with the pre-PTM event here and the main shift. And look, you have clearly some mercury anomalies here and here. And especially it's interesting to see that the maximum of mercury anomaly are preceding the PTM, meaning that maybe the volcanism triggers some phenomena at the beginning. But with volcanic activity, you may explain such things, such negative isotopes shift, but this one is maybe more difficult because still more negative in several places, especially into the sea. Okay, and we have seen the same thing also in Spain. If you move from continent here, this was the last section that I just showed you, to deeper environment, this is the Zumaya section, which is very well known in the world, contain 2 GSSP, a very nice KT boundary, and a very nice PTM, all along the same beach. So for the students, this is just wonderful. You can move from the Upper Cretaceous to the Eocene and see 2 main events, the KT boundary and the PTM. And this is a PTM. And here you can see that the PTM is marked by a change again from carbonate, sometimes turbidite, to pure clay, which means acidification, no more carbonate. And if you run some stabilized tops, you can see here that you have a very nice delta C13 shift. And again, some mercury anomaly here, which predates the PTM, a few ones here, which are not so expressed as in a continental, but it's normal, these are deep sea. So the anomaly has to be lower. And clearly you can, you can correlate these 2 records, one continent, continental one marine, quite easily. So, meaning that there was some volcanic linked to the North Atlantic province, but it's not the only one. Here you can see that there was also a huge volcanic activity in the Caribbean plates. This is a place of very complex subduction. And some people have used some cores here, and they can show, for example, that the number of ash layers, the frequency of these ash layers are clearly increasing during the PTM. So all these things may have had a lot of CO2 into the atmosphere, but with that you cannot really explain more or less this so huge negative shift. The CO2 from volcanic activity is negative, for sure, but you cannot explain everything. And here what I want to show you that there is another trigger. And this one we still didn't see it, but first of all, let's see a few things here. The PTM event is really marked by a decrease of the latitudinal temperature gradient. What does it mean? It means that normally here this is cooler and here than here, okay? And the gradient normally is like that. You have clearly a change of temperature when you go from low to high latitude. And this has changed. As I said, you move the tropical belt to a high latitude, it becomes warmer. And this is a modern subsurface temperature gradient. This is 0 latitude, high temperature, you go to the south or to the north pole. Clearly this is cooler. And people do some modeling, and this is a modern bottom water temperature, so quite cold, the deep water. And during this time, in fact, this sea surface gradient was like these red dots here that you have. So the gradient was a lot more smooth, all was warm, and in fact the temperature of the sea bottom water were really high. And this is very important for the scenario which will follow. Okay, so moreover, during this time, if you increase the temperature of the deep ocean, you will get quite a lot of sea level fluctuation, which are maybe only linked to thermal expansion. If you warm a lot the ocean, you have a thermal expansion of the ocean, you can create this kind of multiple transgression. And these multiple transgressions are quite important because by this way you can transfer warm saline water from the epicontinental sea to the deep sea and warm again the deep sea. Okay, but by now you have really to explain why you have a so negative shift. And here for the first time, and this is Dickens, Zakos, all this team, we were the first proponents to that theory. And this delta C13 is probably linked to the dissociation of the methane hydrate, to the melting of the clatrate. So, as I said at the beginning, there is a lot of place, so I will just go here, we'll go back to that one after. You can see here that actually, all around into the slope at 2 to 3 kilometer depth, you have a huge accumulation close to the surface, around in the first 50 meters of the sediments, you have a lot of methane. Because why? Because you have in the first meter of sediments a lot of bacterial activity which are producing methane. Okay, but at 2 kilometer, 3 kilometer depth, this methane is under an icy state. Okay, these are clatrate. But if you, and it's exactly what it's exactly what happened. You have this gas hydrate stability zone, which are clatrate. They will melt, and this methane will be released to the water. And if you release the methane to the water, CH4, this CH4 will be converted to CO2 by oxidation in seawater. If you have this oxidation state in seawater, it means that the global oxidation will decrease, and you get also some anoxy here, which will add a stress here in this kind of depth of the ocean. And this CO2 will go into the water mass, and after will be added to the atmospheric CO2. And this destabilization could be fast, very fast, in fact. It's a question of maybe 1,000–2,000 of years. You have to warm this deep ocean, and I told you that it was possibly the case because you have this pre-TM event due to volcanic activity, which may have warmed the deeper ocean. But we have some proof of that, because a lot of people are always arguing about this methane release without really bringing some more evidences. And here's the interesting things. Well, this picture here, this normally a movie which doesn't work, but these are bubbles of methanes which are expelled along all these slopes here. What you see here, this is a PTM, and you can see that this is a seismic line, and you can see there is a chaotic zone, and this chaotic zone is explained by this the melting of the clatrate. Because if the clatrate, methane clatrate, are present into the sediment under an icy state, and when they melt, they will clearly disturb all these sediments and create this kind of chaotic zone that you can see, for example, close to Florida. And this is more or less a place where you have sediments which are quite disturbed, which could be quite a nice proof. Our proof also is sometimes the presence of methanotrophic bacteria in organic matter-rich sediments, which are coeval to the PTM, meaning that you have methane activity during this term. Another source, potential source, And this will be maybe a project that we want to launch here, to launch in India. This is the fact that maybe the methane source could be subduction zone. And here, for example, this is an example in Alaska, where, well, it may be possible that if you have a lot of organic matter, it could be the same for the CO2, a lot of methane, and you have a subduction zone, this can be also more or less released to the atmosphere. I think there is a problem here. This is the timing of the process. It's a quite slow process. And apart in India, the global tectonic activity at the end of the Paleocene is quite slow. But in India, there is the subduction zone, and maybe what we will look are sediments in Himalaya, where you can make some estimation, for example, of the potential organic carbon content, and make some modeling to trying to see if we more or less subduct sediments enriched in CO2, how much CO2 you will get through the methane vent and so on. I'm not so sure about that. We did quite a lot of models here, but it doesn't really work so much. But for the North Atlantic Sea, some people like Svensson from Norway have seen very nice things here. What he have seen, these are hydrothermal complex van here, and these vans are crossing again some evaporite and some coal-rich things, and can also evidently release the methane via these hydrothermal pipes, which may explain the onset of the global warming. So, another proof, we already discussed this yesterday. These are the fragmentation index, the acidification. And here, this is a work of one of my former PhD students, Aidan Mort. This is a guy who worked about the phosphorus regeneration during Cenomanian and Turonian that I showed you yesterday. This is his master thesis, in fact, and he starts with the Paleocene-Eocene. And what he showed very nicely that, well, during the Paleocene-Eocene thermal maximum, corresponding to this negative shift here, you have here an increase in fragmented or fragments of foraminiferous, decrease of complete foraminiferous, which again speak in favor of a huge acidification during this time. Since people have used different kind of isotopes, like boron isotopes, showing evidently that there was a lower pH, because boron isotopes vary in the shell of foraminifera in function of the pH. So there is another way to show that. So it's really interesting. You can see that these very nice negative peaks is very sharp, and this 5 to 6 per mil negative excursion cannot be explained if you don't add an external source in order to get so negative values. And this external source of carbon, of light carbon, would be the methane. And by this way, you can explain this huge shift. A very nice paper has been published in the 2005, I guess, years. This is by Zakos. And here what he showed very nicely, it's another evidence of the solution acidification. And I think what he did is very, very clever. This is, you see that this is some kind of a rise here. It's a submarine mountain chain, if you want. And what they took some cores at different depth here, with increasing depth. And here you can see that you have, something which was at almost 5,000 meter depth. It's more actually. It was been probably less deep, but still this was deeper, deeper, and deeper. Okay, and this is the Sakski rise here. This is a place where these things have been taken, and what he shows is sorry, I have to go back. What is shown is very nicely that you have a lag here between all these cores. So you can see that you have a dissolution event here, 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 and here. And this dissolution event has a lag in time. So it means that you have here between 3,000 meters and 5,000 meters, almost a 2 kilometer shoaling of the CCD, the calcite composition depth, due to the fact that you have a lowering deep sea pH, okay? And this really speak in favor of clatrate methane dissociation, because if you increase the CO2 in the deep water, you will lower the pH. This is a very nice paper. Okay, now we are about quite close to the end for the PTM, and we need now to get a bigger picture of what happened. And these bigger pictures is quite close of what we get for the actual warming, as you will see. First of all, the contribution of methane hydrates to this global thermal maximum is a very nice positive feedback loop. I told you that positive feedback, this is just an acceleration of the phenomena. And here, the trigger of this acceleration of the warming is the methane hydrates, as, for example, the greenhouse gas that humans are emitting actually. So that's why a lot of people are doing that comparison. So we have a reduction of the sea surface temperature. So it means that you increase density of the water, and meaning that warm water will sink, okay? This warm water will sink and warm the deep ocean. If you warm the deep ocean at 2 or 3 kilometer depth, what will happen? It will happen that the icy stage of the methane will not exist anymore. It means that you will dissociate the clatrate, and the methane will go, will melt, the clatrate will melt, and the methane will go into the water column. And this leads clearly to the deep benthic foraminifera extinction, because this guy clearly has some problem, very less oxygen, and there is anoxic condition and acidification, in this case, at this stage. And after you release the methane, and this methane will be transformed into CO2, creating water column anoxia, which is clearly not very good for the deep benthic inhabitants. And this CO2 will be injected into the atmosphere, and clearly you accelerate the global warming. And if you have the global warming, you will have the change, biotic change, and increasing chemical wearing on land, because you increase the greenhouse condition. So biotic change, I remember it's disappearance of bed and benthic foraminifera, but as you have warm water with nutrient, you have also at the surface at least more plenty foraminifera, but especially on land you have a lot of biotic change due to the fact that you change a lot the climate. And this clearly accelerate as a feedback. And now the question, and this is the main question that we have to discuss this afternoon: how do we stop this kind of phenomena? Here you warm, you warm, you warm. And here, well, this is an hypothesis of Baines. Well, it's probably, I'm not sure that everything can be really checked here, but I think it's a very nice hypothesis. It's quite controversial, but the possible model is the following. Okay, so you have, this is the sea, okay? You have the release of, in the deep ocean, of the methane. What would happen? For sure, if you do that, you have more CO2 in the water and high dissolution. So it means that in the water, you have a nice, very high content of dissolved carbon. Very, very high. And what happens here at the surface, this is more and more, let's say, warm. So you will favor at the surface some bloom of nanoplankton, especially because if you are greenhouse condition on the continent, you will add more and more nutrient. And clearly, all these animals will take all the dissolved inorganic carbon to build their shell, okay? And in fact, if they do that, it's a sequestration of the carbon by an acceleration of the oceanic biological pump, okay? And this is really a way to draw down the CO2 by carbon sequestration, by burial, okay? And this probably has been quite helped by the fact that on land you have more humid climate condition, more weathering, and you have this nutrient increase. So you increase the productivity. So it's probably a way to stop this phenomena. Now the question is, well, could we really compare that? We will see this afternoon if we can really compare these things with the actual warming, and if we can stop this actual warming. I can say very quickly, probably no, because the actual biological pump in the ocean is not working so well. So the regulation of the climate or CO2 pressure by the ocean by now is not so effective. So in fact here this is what I was talking about at the beginning, the very beginning. This is this famous Gaia hypothesis, meaning that you have an auto-regulation, a self-regulation of the biosphere by the Earth. This is a Gaia hypothesis in these books of James Lovelock. And that's for sure. There is a self-regulation on Earth in the past. And all the examples that I show you clearly show that we can be optimistic, because the recovery always happens. But by now, you will see the difference this afternoon. I guess that the speed of the change is something which is completely unique. You increase the greenhouse so fast, but I am not so sure that this kind of recovery may occur so easily. Okay, so this is a small cartoon explaining what was PTM at this period. So if we start here with the phase 1, you can see that we have a gradual warming during the late Paleocene, and you sink the warm saline water, and you get your warming of the deep ocean, and you start, oh, there is a problem here. And you start to release the clatrate methane. What happened? Ah, sorry. Okay, there's no problem. And you release hydrate methane, and this probably the starting point here is volcanic activity, especially the North Atlantic provinces. But we can discuss this later on. But I guess that there is more volcanism, and we were really asking them if also all the volcanism, which is linked to the subduction in India, which more or less was operating in the same time, could be also responsible of some mercury anomaly. Why? Because we have mercury anomaly in Egypt, in Cameroon, and also in Pakistan. So I'm really asking them if there may be also some volcanism in India working at the same time. So, and what you get here, it's a huge warming, and well, dissociation of the midrate and you get acidification of the ocean, and you get the depth of the mid-Baltic foraminifera. But on land, you have more and more vegetation. You have the migration of the mammals and the origination of a lot of new species, and an intensive silicate weathering. And here, this is a recovery where, in fact, well, the quantity of dissolved inorganic carbon into the ocean will be used by algae which are blooming, the nanofossils are blooming, and with the help of nutrients, we recover from that situation. So, in fact, it's one of the best examples of feedback loops, if you want. And this is very important because this kind of feedback are really triggering the change on Earth, especially by now. And here this is a block diagram from a guy who was at ETH, Weissert. And what he showed clearly, well, nothing new. In fact, this is just a sum up of many, many papers. But you can see here you have the CO2 greenhouse warming. This greenhouse warming will warm the deep water. You will melt the methane hydrates, the clatrate. You have the methane release. This methane release will create anoxia in the deep water ocean as some extinction and will be transformed into CO2. And this CO2 go into atmosphere and will amplify the greenhouse effect. But by this way, this is really a very nice positive feedback. But afterwards, what you get, in fact, is a very nice negative feedback, which is linked to the fact that this has been stopped and the CO2 has been dragged on because here you have a lot of dissolved organic carbon which will be used by, for example, algae, and you have sequestration of the carbon by burial. This is a very super activation of the biological carbon pump, which is helped by the arrival of a lot of nutrients from the land. Okay, so this was a little bit what I have to say on the PTM. And yeah, these are a few conclusions. Well, this took place around 55 million years ago. These are, the Eocene was the last period up to now, which was really warm. And by now we are living in an ice house period, but I don't know for how long, because now we are melting really Antarctica and Arctica in the same times, which is really very problematic. And this is probably of one of the most dramatic geological confirmation of greenhouse theory. And also, well, that increasing CO2 into the atmosphere, but also increasing methane from the permafrost, from the cattle activity. It's better to be vegetarian by now, I guess. You have here clearly a proof that CO2 is warming the Earth's surface. And interestingly, that very large release of organic C13 depleted carbon caused really a huge carbon isotopic negative excursion, acidification, carbonate dissolution, and aloxia in the deep ocean. And this carbon was removed from the exogenic pool on a time scale of, let's say, well, it's difficult to say, but at least 100,000 years, through silicate weathering and through the activation of the super activation of the biological pump from the ocean. So, okay, this is really interesting because I think that this warming is really linked to the PCO2. So, meaning that we can take this as an example. And I think research of PTM, if this is the last conclusion that you have here down in yellow, it's really a rapid global change, which more or less make things the people that could be a very good example for the future anthropogenic warming. But I think we need a lot of work to do that. And as you will see, if you compare more or less the quantity, the amount of CO2 which has been emitted during this event with the one that we are emitting by now, still, this is not comparable. And this is a big problem because everything is faster by now, as you will see this afternoon. So, okay, so I have finished with this PTM. So here, if you have any question, don't hesitate. And for this afternoon, I will present you the Anthropocene. We can start, yes, at 2 o'clock. So be there a little bit before, please. And after, I just want to start the discussion with you. First of all, I just want some feedback of the course. I know it's a lot of information at the same time. It's not always easy to understand, but if you already have 25% of the knowledge that I'm trying to transmit, this is not so bad. And just to understand that you, students, from all the world, you are the people which may solve this kind of problems, and for that you need a good knowledge of the history of life. If you don't have this knowledge, you don't really understand what is happening by now. And I don't want to be pessimistic, but I think that if you are doing nothing, and it's really quite crucial, because by now you will see this afternoon we have numbers, and I think that only stupid people like Trump and others are thinking there is no warming due to human activity. But we have still a lot of people thinking that, especially the people who want to do some money, because clearly if you have to take, let's say, some decision about ecology, about the way to live, this will lead to a drastic change in our way of life. But I don't think that we have any choice here. And you as students, and what I think that all these things need education. You need to be aware of the problems. And don't forget that more than half part of the American people are still believing that the earth is flat. So this is something which is, for me, I'm puzzling, really puzzled by that, because it means that a lot of people are just missing of education. And you, I think you have the chance to be there and to try to change the things. I will not say that it's easy to change the things, but at least only the fact that you start to understand how the things are working, you can get probably some solution. And as you will see this afternoon, the things are going very fast, and we will face in 100 years, for example, a really big problem if we don't take care. Okay, so this afternoon I will show you a little bit what happened in the Anthropocene, and after we can have a discussion about the paper that this is this nature paper that I asked you to read. I hope that you did it. And after we can have a small discussion. And as I say, this is almost the day of election. I want a vote at the end in order to, it will be a question. And the question I can say you, do you really think that it's really necessary to fix the beginning of the Anthropocene and to use the Anthropocene as a geological stage, or we don't need that, or this is not very useful? You understand why to do that or not? And this is a little bit the question that I have at the end, and I think at the very, very end you will get some diploma for the course. I am right? Okay. So don't move. Okay, so see you in, yes, at 2 o'clock. Okay.